Hey guys, welcome back to day 23. We'll talk about electronegativity and polarity. So first, let's define electronegativity. It's the ability of an atom to attract electrons to itself. Linus Pauling came up with this. And it's just an intrinsic ability of the atom to draw electron density to itself. The top five electronegative atoms are 1, fluorine, 2, oxygen, 3, chlorine, 4, nitrogen, 5, bromine. So here's a chart of the trends of electronegativity, and as you can see, the top 5 are purple here: fluorine, oxygen, chlorine, nitrogen, and bromine. Fluorine would be the most electronegative, and if you kind of look, the trend goes to where francium would be the least electronegative. And it kind of makes sense because we know if fluorine gains an electron, it's isoelectronic with neon, and it's stable. If francium gives up an electron, it's isoelectronic with radon, and it's stable. So those are the trends. If you notice, the noble gases are not there. That's because they're hard. They do not pull electrons to themselves, and they do not give up electrons. So when we talk about electrons being pulled to an atom, that means a bond. If I have X bonded to Y, this means that those electrons, these two electrons here, they're not going to be shared evenly, potentially. So a polar bond uneven distribution in electron density between the two bonded atoms. So that means we're not evenly sharing the electrons. The electrons are not spending the same amount of time around both atoms, more on one atom than the other. A polar molecule has a net dipole moment. Where the overall electron density of the molecule has an uneven distribution and there are two poles of charge. So both shape and negativity play a role in this polarity. And we'll get to that once we cover the shapes. Now let's talk about the bond types. So in the continuum of bond types, we have pure covalent, or totally evenly shared, polar covalent, or we're unequally shared, and then ionic. And as you can see, it's a range. Just like speeding's a range. If I'm going 46 miles an hour in a 45 mile an hour zone, I'm technically speeding, barely. If I'm going 80 in a 45 mile an hour zone, I'm really speeding. So there's a difference there. One, if I'm going 46 in a 45, I get pulled over. If I get a speeding ticket, that's kind of more, I don't know why. I don't think that would actually hold up, a 46 and a 45. A 55 and a 45 will hold up as a speeding ticket. 90 and a 45, I'm probably going to jail. So there's just a continuum of speeding there, or how severe the penalty is going to be. Similar to electrons being shared. So we can evenly share, like F2, there is no uneven sharing there. F2, O2's here, or CH considered a non-polar equally shared bond. And the difference of the electronegativity is 0.4 because carbon was 2.5 and hydrogen's 2.1. When it comes to polar, there's a couple we can throw out there. So for polar, if I have carbon to oxygen, that would be 1.0. That would be a polar bond. C to O. O to H is a little bit more. OH, polar. About as polar as we get is HF. And when it comes to ionic, right, NaCl is here, and cesium fluoride's over there. That's ionic, completely ionic. We're concerned whether we're in this range right here, where we're polar bond, or if we're in this range right here, evenly shared. So how are we going to classify these? Do I need to memorize all those electronegativity numbers? No. So for ionic, we are still going to consider ionic compounds opposite sides of stairs. So if it's on the opposite side of the stairs, we're still going to, metal, non-metal, still going to be ionic, regardless of what delta En is. And we're going to be good enough for our course. Polar is going to be if I have a top 5 electronegative atom bonded to anything else. We're going to consider that a polar bond. And then everything else will be non-metal bonded to another non-metal. It's going to be equally shared. Let's do some examples now. So which of the following have a polar bond? H2. So that's H bonded to H. Is that polar? Well, is hydrogen a top 5? No. And hydrogen is hydrogen, so the electronegativity difference is 0. So that would not be a polar bond. HF, F is a top 5. So that means we have a polar bond here. F is a top 5, but when F's bonded to F, delta En is 0. So that's not polar. H2O. Oxygen is a top 5. So it looks like we have 2 polar bonds. Carbon tetrachloride. We have Cl as a top 5. So it looks like I have 4 polar bonds. And that's it. Because do I have a top 5 bonded to not itself? And then you know if it's polar bond or not. It doesn't mean the molecule is polar. It just means that the bond is polar.